Let's do this example. The elevator in the car rental building at San Francisco International Airport has a placard stating that the maximum capacity is 4,000 pounds with 27 passengers. This converts to a mean passenger weight of 148 pounds when the elevator is full. 4,000 pounds divided by 27 passengers, and we get 148.15 pounds. We're rounding it to 148 pounds when the elevator is full. We assume a worst case scenario in which the elevator is filled with 27 adult males. Assume that adult males have weights that are normally distributed with a mean of 189 pounds and a standard deviation of 39 pounds. A, find the probability that one randomly selected adult male has a weight greater than 148 pounds. First, can we use our normal standard distribution? Yes. Here it says, assume that adult males have weights that are normally distributed. That means for A, I can use my regular normal calculator. I go to Stat, Calculators, Normal. The mean is 189. The standard deviation is 39 pounds. And I want to find the probability that a man has a weight over 148 pounds. Because if I have 27 adult males piling into an elevator, I want to know what's the probability that it's going to be more than 4,000 pounds inside of that elevator. For A, our probability is equal to 0.8534, or 85.34%. That's a pretty high percent that we're going to have too much weight in that elevator, isn't that? If we look at the mean of 189 and a standard deviation of 39, and here's 148, a lot of adult males weigh more than 148 pounds. That's probably not safe. I use Statcrunch. Here we're dealing with individual value from a normally distributed population, so we seek the area of the red shaded region in the figure. The first thing we could do is convert the weights in using a z-score and get x minus mu over sigma, where we have 148 is what we're looking for, minus 189 divided by 39 is equal to negative 1.05. And we want to find all x values greater than negative 1.05. And this is the value that we get if we convert to a z number first. Here, I didn't convert to a z number first. I just said the mean was 189, the standard deviation is 39, and I want to know what the probability is that these men weigh 148 pounds or more. And we get pretty much the same answer. If I would have taken this z number out to a few more places, they would have been exact. Now we want to go back and talk about B. For B, find the probability that a sample of 27 randomly selected adult males has a mean weight greater than 148 pounds. Now this is different because now instead here we selected one adult. And here we're selecting a sample of 27 adults. For this one, can we use the central limit theorem? Well, yes, we can, because we already know that the weights are normally distributed. That works out perfectly. The only thing we have to do different, we know the mean is going to stay the same, but the standard deviation is going to equal the original standard deviation divided by the square root of n, which here n is equal to 27. If we go back here, we have our mean as 189. our standard deviation is wrong. Our new standard deviation is 39 divided by the square root of 27. And that is equal to 7.5. I'll just round it up to 5.1. We still want to know the probability that the men weight are greater than or equal to 148 pounds. Almost everyone. The probability that X is greater than or equal to 148 pounds is equal to 0.9999. Basically, it's approximately 1 or 100%. We can use the normal distribution if the original population is normally distributed or n is greater than 30. N is not greater than 30, but we were told that the original population is normally distributed. Because we are now dealing with a distribution of sample means, we must use different parameters, mu of x sub x bar and sigma sub x bar. And we want to find the green shaded area. We did, and we got the same value, which is basically 100% of the people. So interpretation. There is a 0.8534 probability that an individual male will weigh more than 148 pounds. So if we just pick a man, there's an 85% or 0.8534 probability that that man weighs more than 148 pounds. However, if we select 27 males randomly, the probability that the selected males will have a mean weight greater than 148 pounds. It goes up to almost 100%. Given that the safe capacity of the elevator is 4,000 pounds, it is almost certain that it will be overweight if it is filled with 27 randomly selected adult males. That's important to know. So something went wrong. We should not put safety measures on an elevator that's not safe. Do one more. Let's write things down as we go. Assume the population of human body temperatures has a mean of 98.6 degrees Fahrenheit, as is commonly believed. Also assume the population standard deviation, sigma, is equal to 0.62 degrees Fahrenheit, based on data from the University of Maryland researchers. If a sample of size n is randomly selected, now we're talking about a sample, and the sample size is 106, which is greater than 30, so we're in good shape. Find the probability of getting a mean of 98.2 degrees Fahrenheit or lower. First, let's figure out what we need. We need our mu sub x bar, which is the same as our mu. But our sigma of the mean of the sample is equal to 0.62 degrees Fahrenheit divided by the square root of n, and n is 106. That gives me a value of 0.06, and let's change our values. Our mean now is 98.6. Our standard deviation is 0.06. We'll want to find out the probability of getting a mean of less than or equal 98.2. And we hit compute. And that number is 1.3084. What E means is actually scientific notation. It's the same as saying times 10 to the negative 11th power, which is the same as taking this value and moving our decimal place 11 places to the left. 1, 2, 3, 5, 6, 7, 8, 9, 10, 11. That would be our value, which is 0%. or 0 probability. Let's see what that means. If a sample size of n equals 106 is randomly selected, the probability of a mean of 98.2 degrees Fahrenheit or lower is really pretty much 0. We work under the assumption that the population of human body temperatures has a mean of 98.6, but because the sample size is n equals 106, which exceeds 30, we use the central limit theorem and conclude that the distribution of sample means is a normal distribution. Our sample size is big enough to use the central limit theorem. And just like we did before, our mu is the same. Our sigma sub x bar, we had to divide by the square root of 106, and we got this tiny, tiny number. That concludes the PowerPoint part of the presentation.